know that many people are still traveling back. Several of my students are traveling back, and tomorrow the forecast is for a snowstorm here, so they don't get stuck. Good work. But anyway, usually I introduce the speaker. So I'll introduce the speaker. I'm Yoram Rudy, and I'm happy to have you all here today. And what I would like to, I think many of you know about the work that we've done over the years on modeling cardiac cells and ion channels and the mechanisms of arrhythmias at the level of the ion channel cell and tissue. What I would like to cover today and describe today is a totally different project that's taking place in my laboratory that is called Electrocardiographic Imaging. And it's the development of a non-invasive imaging modality for cardiac electrophysiology and arrhythmias. It's been in development for over 20 years now. And I'm very grateful to the NIH for having so much faith in me that they gave me this merit award that seemed to last forever, but now it's almost time to renew it. It's not for nothing. So, to get started, I think everybody here knows that cardiac arrhythmias are a major cause of death and disability. But it's good to take a step back and look at numbers. The prevalence is 3.9 million per year, and mortality, that's a low estimate. It's about 325,000 per year. It's the latest number I heard from Peter Spooner when he was still at the NIH in the US. But most people will say it's more like 400,000, 450,000. The mortality is estimated to be 7 million per year worldwide. And of course, many more people are disabled and have a very compromised quality of life. So it's a major clinical problem. The current methods for non-invasive diagnosis, and we all know that there are methods for invasive diagnosis that involve catheterization and getting into the heart through the venous system. But the current method for non-invasive diagnosis is the ECG. And the ECG has not changed much since the days of Eindhoven. We don't force people to put their hands in cold water anymore, but still what we do is we measure potentials on the body surface, either the extremities or the chest, far away from the heart. And of course, being far away from the heart, it suffers from many problems and limitations. For example, it lacks sensitivity. It cannot detect arrhythmogenic substrate in many cases. There could be arrhythmogenic substrate in the heart, but because of the remoteness of those electrodes on the body surface, it's not reflected in the body surface electrocardiograms. Or not sufficiently early to prevent deadly arrhythmia from occurring. It also lacks in specificity. It cannot provide specific diagnosis as to the mechanism of an arrhythmia. Is it a focal arrhythmia or reentrant propagation involved? And it cannot specify the mechanism for specific therapy. If the mechanism of an arrhythmia involves slow conduction, there could be another approach for therapy than one that involves automatic pacemaking for a group of cells that are diseased. So all of those are limitations because of the ECG. And don't take me wrong, the ECG has been, of course, very useful in diagnosis and treatment of heart disease. But we have to move forward, and this has been without a doubt. 2 years ago, we celebrated 100 years to the invention of the electrocardiogram in Holland, the birthplace of Eindhoven.
Yoram, can I ask you a question about this picture? You want us to interrupt you with a question?
Yes.
Go back to the picture of the guy with his hands. I have a historical question.
Yeah.
What is the
I don't know if I know historical.
Okay, well, then you have to ask Igor.
Yeah, Igor is an expert on the history.
There seems to be two buckets, and what is the purpose? Do you know what the two buckets are in the setup?
Here?
I don't understand the principle of how this setup is working here. Why do they have the two buckets? I've always seen.
You mean here?
Yeah.
Both.
And all of them have two buckets in it. So he's got an inner chamber and an outer chamber. What's going on? You don't know.
all I know, these are electrolytic fluids, seawater. Right? That's all it is. Saline solution, seawater, that conducts electricity, and you put your hands in there and you have contact, and then somehow it's connected to a galvanometer. Why do they have two?
Does it have to be cold?
doesn't actually have it. Doesn't have to.
Okay,
It
anyway.
reminds me, there was this. Okay, I think, sorry, we can continue. That's okay. All right, so electrocardiographic imaging, ECGI, is intended to overcome those limitations. Non-invasive imaging, by the way, the first electrocardiogram to be taken in England by Sir, what was his name, Wyland. And that was done, your place, and that was done on a dog. And they showed a picture of the dog, I think in the newspaper, with his legs in buckets of water. And that went all the way to the House of Lords. And he was brought into an investigation to say, this is cruelty to animals. You make the dog stand in seawater. So I think his response was, and that's documented, I can find it for you, his response was, I recommend that the members of the House of Lords, the distinguished, whatever you call it, members will go to the seaside and bathe in the water and will tell me if this is suffering or not. So that's a story. Anyway, electrocardiographic imaging, ECGI, non-invasive imaging is a cornerstone of the practice of modern medicine. I think nobody here can imagine the practice of modern medicine without CT, MRI, or ultrasound. But there is no non-invasive imaging modality for cardiac arrhythmias. And what I mean by non-invasive is not measurement on the body surface, but measurement on the body surface and then reconstruction from the body surface non-invasively to the surface of the heart. That is imaging, and that does not exist yet for cardiac arrhythmias. So over 20 years ago or longer, we were set to make it happen and develop an imaging modality, which we call electrocardiographic imaging, or ECGI, and is a new imaging approach that reconstructs potentials, electrograms, and isochrones on the heart surface. Electrograms are the equivalents of electrocardiograms. Electrocardiograms are measured by an electrode on the body surface. An electrogram will be measured on the epicardial surface, above the surface of the heart. If you put an electrode there, it will measure a signal similar to the electrocardiogram, but from the surface of the heart. And then isochrones are equitime lines, or the activation sequence of the excitation of the heart. And all of those we were set to reconstruct non-invasively on the heart surface without the need to penetrate the heart. So a little bit about the theory behind it and the mathematics of it, and I'll go over it very briefly. The volume between the heart and the body surface is source-free. That is, there are no electrical sources. There are no electrical activity of muscle between the heart and the body surface. The lungs are not electrically active. It's not an excitable tissue. And therefore, the electromagnetic field is governed in that volume by Laplace's equation that is shown here. You can take Laplace's equation and use what's known as Green's second theorem, which transforms this differential equation into an integral equation. It relates integrals of the potential phi, shown here, of the electrical potential phi, over the heart surface and the torso surfaces. We can then take those integrals over the two surfaces and use the boundary element method to discretize them. And we end up with a matrix equation that you see here that relates the torso potential, phi t, to phi e, which is the heart potential, and there is a matrix of coefficients that includes the geometrical relationships between the two. And when you multiply the vector of potentials on the heart, on the epicardial surface of the heart, by this transformation matrix A, which includes the geometrical relationships, you obtain the body surface potential. Obtaining torso potentials from heart potential is known as the forward problem, because the heart generates the electrical activity, and then you go forward from there to compute potential on the torso. That's called the forward problem. In contrast, to go from potentials on the torso deep into the body back to the heart is known as the inverse problem. And the inverse problem has some difficult properties mathematically. This is what we have as a forward problem. Given the potential on the heart, we obtain potentials on the torso. But in order to obtain this from this, which is the goal of electrocardiographic imaging, we have to invert the matrix A. We multiply by A to the minus 1, there is not 1 here, and A minus 1, now we'll multiply the torso potentials to give us the potentials on the heart, which is what we want. But we cannot do this because this problem is ill-conditioned or ill-posed. And the matrix A has very bad properties that do not allow simple inversion of that matrix. The problem is ill-posed. You cannot just simply invert that matrix. So what we've done, we use two different approaches to overcome this issue. One of them is known as Tikhonov regularization. And in Tikhonov regularization, instead of solving this solution, this problem here, we minimize this functional here. Minimize, that is, we find phi, the potentials on the heart, that will minimize this expression. This expression has two parts. This part here, of course, is an approximation to the solution of Laplace's equation, because when this is 0, A phi E equals phi T, which is our original equation, which we cannot solve. This term here introduces a constraint on the potentials on the heart. For example, the constraint L could be unity. That means we put a bound on the magnitude of potentials on the heart. We say that the potentials on the heart cannot exceed 1 volt. We know they cannot exceed 1 volt. They definitely cannot be 100 volts, otherwise our heart will light the house. But potentials on the heart are limited, and we know what is the limitation and how high potentials can get. So one possibility is to put a constraint and find the best composition, the best mixture here that will give us an approximation of solution to Laplace's equation, subject to a certain constraint. Now the T is the regularization parameter. It determines how much of the mixture is regularization, is constraint, and how much is approximation to Laplace's equation. So that is one approach. The other approach is called general minimal residual method, or GMRES. And unlike the previous method, which was a constraint-based method, this method is a method of iteration. It's an iterative approach. What we do is we approximate a to the minus 1, which we cannot compute, by a polynomial P of A, and we solve this equation. Phi E equals now P of A, phi of T. P of A, phi of T, I cannot really get into all the details, define a Krylov space K, which has very nice properties in terms of iterations. Most importantly, it provides nice properties in terms of convergence. So after several iterations, we know that the residual A of E minus phi T, which we want to be as close to 0 as we can, which will give us the correct phi E, decreases with each iteration. And then we stop the iterations when we are having a phi E that is lower than a certain, the residual here is lower than a prescribed specified number, or we stop at a certain number of iterations that exceeds a certain maximum. So during those iterations, one after the other, we choose the best iterate, we know it converges, and the best iterate will give us something close, a very good approximation of the potentials on the heart. Okay, this is as far as I want to get into the mathematical methods. I know that it doesn't give you any of the details, but I hope it gives you some impression of the difficulties involved and what we have done. So now to the physiology and normal cardiac excitation. Well, everybody knows in this crowd, I'm sure, that cardiac electrical activity starts from the sinus node here and spreads radially throughout the atria. It then penetrates the conduction system, the Purkinje system of the heart. And what travels are action potentials that have different shapes in different parts of the heart. And when they travel, they generate the electrocardiograms on the body surface and the electrograms on the heart surface. For normal cardiac excitation, this is taken from Durer classic study in 7 normal human hearts that were isolated from people who died from reasons other than heart disease, such as motorcycle accidents. So presumably these were normal hearts. They were isolated, but they were normal hearts. And you can see that in normal hearts, an activation wavefront is formed parallel to the cavities. This is the LV cavity, left ventricle, right ventricle. And in both of them, early on, these are times, these are isochrones, so these are the activation fronts. And the activation spreads from endocardium to epicardium very uniformly in the left ventricle and the right ventricle. Important events are, for example, the breakthrough of the activation front on the heart surface, on the epicardial surface, an event known as epicardial breakthrough. So the arrival and break of the wavefront on the epicardial surface of the heart is indicative of cardiac activation, normal or abnormal. Okay? The other thing that I wanted to mention is cardiac arrhythmias. And very grossly, cardiac arrhythmias can be divided into two types. One of them is ectopic arrhythmogenic focus. So instead of the sinus node, a group of cells that is abnormal because of disease is now taking control of the heart rhythm and become the unwanted abnormal pacemaker. And then, of course, the heart doesn't function normally, it doesn't contract in the normal sequence, and not a good story. The other possibility is what is called reentry. The action potential now start to travel in a closed pathway. Instead of forming those very broad wavefronts or very radial wavefronts in the atria, this could be in the atria or the ventricle, instead of traveling in broad, uniform, and planar wavefronts, the action potential now forms a closed loop known as a reentrant loop, and it'll go around the loop over and over and over again, becoming an oscillator that will now take control from the sinus node, will radiate activity in all directions, and you can think about this now as becoming the pacemaker, if you will, that drives the heart. Again, it could be here, it could be here, and under severe conditions, this will break into multiple reentry pathways that will asynchronously drive the heart in many different places. So the heart, each part of the heart, will be driven to its own drumbeat, so to speak, and that's called fibrillation, complete loss of synchronization. So focal activity or reentrant activity, both of them are arrhythmogenic. They take control from the sinus node and drive the heart in a very abnormal fashion so that contraction is not efficient. Okay, so now I told you about the mathematics behind it and why we wanted to do it. But before it can be applied in people, you have to go through a long and detailed period of validation. As I said, the mathematics is very complicated. It's very prone to error. The ill-posed nature of this mathematical problem makes it very sensitive to error. Very small errors in measurements can be amplified when we go back to the heart. So we have to make sure that what we are doing is correct by validation. And validation was done over many years, and that was the process that took the longest. In this torso tank experimental setup in collaboration with Dr. Bruno Tecardi at the University of Utah in Salt Lake City. And what you see here is a torso tank. You can see the tank here, okay, made from some plastic material that was molded on a 10-year-old boy. And inside, there is an isolated dog heart. The reason it was a boy 10 years in age is because we wanted to make sure that the geometrical relationship is like the adult heart to the adult torso. So the dog heart is smaller, a 10-year-old boy gave us the correct ratio. And so you see here the torso, the heart is embedded. You can see the heart will be embedded right here inside the torso. And of course, we'll generate electrocardiograms on this plastic torso. We'll generate electric field, just like hearts do in this model of the human body. There are many, many rods that carry electrodes on them. And you can push the electrodes against the heart to measure potentials from the tip electrodes that are now measuring electrograms from the heart surface. Okay? So we have measurements directly from the heart surface. And simultaneously, we can measure from the torso surface at all of these electrodes, okay? These electrodes here are at the body surface. So we have measurements on the body surface simultaneously with measurements on the heart surface. The measurements of electrocardiograms on the body surface is the non-invasive input for electrocardiographic imaging. The measured potentials directly from the heart simultaneously, exactly for the same heartbeat, under the same exact conditions, provides us with a gold standard for evaluation and validation of our approach. So we have a gold standard, we have the input, we know the geometry, and we can now start to validate this electrocardiographic imaging methodology. And I wanted to show some examples from these 10 torso experiments before I go to show you results from human studies. Here's a case of infarction. This is the isolated dog heart. The left anterior descending coronary artery was occluded to create an infarct in this region here. And Rick Schussler can tell you more about this because he does this a lot. But it was occluded here, and then octanol was injected. Octanol or ethanol, or one of those, to cause necrosis. It takes about 2 hours after ethanol injection to cause necrosis, to cause a local infarction. We wanted to do it that way, acutely, so we can measure before infarct and after infarct in the same heart. Okay? So what you see here in green are all measured directly from the heart, measured electrograms. Okay? And I chose to show 3 locations. The location here is far away from the region of the infarct, so shouldn't change by the infarction. And these two, this location and this location, are in the infarct. And we verified that the infarct was there by doing histology after the experiment. Okay? So we expect this electrogram here not to change. I'm sorry, to change. And this one here to change. But this one, the control away from the infarction, not change. Measured non-invasively, ECGI computed. This is measured and non-invasively ECGI computed. This is normal before infarction, and this is after infarction. So first of all, you see that in the normal case before infarction, the reconstruction is pretty accurate. You see that the electrogram shows a typical RS morphology with very sharp down deflection here that signifies this is the time of local activation. When you reconstruct isochrones, you take all the times of the steepest descent. This is the time of local activation. You see it's pretty healthy electrogram that shows this typical RS normal morphology, and it's nicely reconstructed non-invasively using ECGI. If you look at this electrogram and this electrogram here, before infarction and after infarction. This one, of course, that is far away from the infarct stays the same. Okay? And the same thing is reconstructed, no change. Okay? Because it's remote to the infarct. These two change drastically. For example, here you can see that there is really total different appearance to the electrogram. What's important to see is the electrogram has an envelope of totally negative potential, pure, which is characteristic of an infarct and dead tissue. But superimposed on it is a small local RS deflection, presumably because of activity in an island of viable tissue. And all of that is reconstructed very nicely, non-invasively with ECGI. Here you see the same behavior. From a healthy RS morphology, it turned into a Q wave, negative morphology with a very small local deflection, presumably again due to surviving islands of viable myocardium. And you can see it's not exact, but it's very similar, reconstructed non-invasively using electrocardiographic imaging. Yes.
And the computed reconstruction is done without any attention to the actual electrocardiography.
Yeah, we take the potentials on the body surface, we take the geometry, we reconstruct potentials all over the heart every millisecond throughout the cardiac cycle. We then collect every millisecond on the same point to get the electrogram at that point, and then we just compare it to the measure. We don't know the measure before we...
How sensitive is it to the actual geometry of the heart inside?
It's very sensitive.
So if it moves half an inch one way or another?
We ran studies on this, and we can tolerate errors to about 1 centimeter in heart tissue, but not greater than 1 centimeter, which is well within the range of CT, for instance.
So you can image the heart using that close to see.
We'll get there. Okay, so this is in the 10th torso where the geometry is known. Okay, another example is in a different heart where we had 5-day-old infant. We occluded the coronary artery for 5 days, and then we were able, in the tank torso, we were able to induce sustained ventricular tachycardia due to reentry. You see here in the measured isochrones, these are times, that the activation blocks. There are 2 lines of blocks shown here in black. There is a corridor between them, and you see that the action potential or the activation front now forms a double loop reentry. It goes through this common pathway, comes out of the common pathway, forms a loop, and re-enters. And there is another loop that goes in the other direction. So this is a double loop, or what some people call figure of 8 re-entry. And you see that the same thing is reconstructed non-invasively using ECGI. The same, not exactly the same lines of block, but close. The common pathway is identified, so if you want to terminate this arrhythmia clinically, you would ablate and burn the tissue right here. So you can kill in one ablation the common pathway, and then you treat the 2 loops. You see that, again, the 2 loops are reconstructed, and even details. For example, you see here that the isochrones are crowded when the wavefront pivots around the end of the line of block. That's because of curvature. There is slow conduction, and the isochrones are crowded together. Even that is reconstructed non-invasively, the detail of slowing of conduction as the waveform turns. Okay, so these are just examples of very extensive validation studies that we've done in the tank torso. And now, finally, I want to go into the application of ECGI in human subjects. We first published it about a year ago, or a year and a half ago, in this publication. And here is how it's done in humans. First, we measure the potential distribution over the entire torso every millisecond using a vest, or now here we use strips of electrodes. Up to 250 electrodes are mapped at the same time. We measure it every millisecond. We measure the electrocardiograms with a temporal resolution of a millisecond, and then we can every millisecond construct the body surface potential distribution from this measurement. So this is the electrical measurement. At the same time, we push the patient through a CT scan, and we obtain both the heart geometry non-invasively from the CT, and in the same frame, we obtain also these shiny dots that are the electrode positions on the body surface. We can then construct a 3-dimensional structure from this, which will give us the heart and the torso geometry, and in particular the electrode location. So we have the geometry non-invasively using CT. We have the potentials non-invasively measuring electrocardiograms all around the torso. And then we marry the 2 in this package that really took us the 20 years of development and validation. And that gives us potentials on the heart surface, electrograms at 600 points all over around the entire heart. And then from these, we can compute activation sequences and isochrones. And I wanted to show some examples. So first, normal activation and repolarization. This is, by the way, is a paper that is now in review in PNAS. The future of it, I don't know. But in any event, we did this in 4 males and 3 females to look at normal activation and repolarization. It's basically repeating the Dürer classical study, but in intact, healthy, normal young adults under the effect of neural stimulation. The nervous system is intact, the heart is working and has a load, unlike the isolated heart preparations of Dürer. And we wanted to see whether it gives us similar results in terms of the electrophysiology. So first, the atria. This is the Dürer study, and you see here sinus node, and from the sinus node, these are isochrones, times, activation spreads in all directions radially, and the last area to depolarize and activate is the left atrial appendage. You see here 2 of our volunteers. These were 2 students in the lab, 1 female, 1 male. And you see here the sinus node, you look very similar. The root of the aorta, the sinus node, beginning of activation, spreads in all directions, and the last area to depolarize is the left atrial appendage, just like the invasive measurements. But this is totally non-invasive. Here's another heart, and what's interesting here that the overall activation sequence is similar with the left atrial appendage to be last, but look at the location of early activation. It's very different from this one to this one. And this is subject to more studies that we should conduct. Rick Schussler and other people wrote about this very large complex of the sinus node. It's not a point like many textbooks will tell you in medical school, but the sinus node is a huge complex, large complex, and pacemaker between individual, the location of initiation will be different. In addition to that, we've seen in dog studies and so on that under effects of vagus stimulation, neurostimulation, the pacemaker can jump in the same subject, in the same dog, as far as 4 centimeters apart. So depending on the heart rate, the pacemaker portion of the sinus node that will take control of the heart rate could be in different locations. And I think that's very important to understand. During ventricular activation, we talked about right ventricular or ventricular breakthrough. And what you see here is a schematic that shows the activation front propagating normally from endocardium towards the epicardium. Now, for electrical purposes, for computing and understanding the electrical field generated by the activation front, you can model the activation front and think about it as a layer of dipoles propagating in the direction of the dipoles. So if you're ahead of the dipoles, you see the positive head of the dipole and you will experience positive potentials. If you're behind the dipoles, you'll see the tail, negative tail of the dipole, and you'll experience negative potentials. So as the activation front is propagating towards the epicardial surface, it generates a positive maximum, positive potentials on the surface ahead of it. Okay? This is seen here in invasive measurements in the chimpanzee done by Medispak, who, by the way, will be here giving a seminar next spring. But Medispak did this in the chimp and in the chimpanzee, which is now an endangered species. You cannot do it anymore. You can see positive potentials on the epicardial surface of the right ventricle before breakthrough occurs. Now, when breakthrough occurs, you see now that there is a window or a hole formed in the activation front. If you now look from here, you'll see the tail ends of all of these dipoles, and you expect to have the maximum replaced by or invaded by a very intense local minimum. And that's exactly what you see. At the moment of breakthrough, this positive potential is invaded by and replaced by a local negative minimum. Exactly the same is seen in one of our volunteers, all of them. You see here positive potentials before breakthrough. This is non-invasive reconstruction of one of our normal volunteers in the study. Positive potentials replaced by a local minimum at the time of breakthrough. Very similar to the chimp. We are very similar to the chimp. This shows that the body surface potentials and the EKG is not sensitive and does not give you any specific details. For example, this is body surface potential measurements from one of our volunteers. This is body surface potential measurements from another volunteer. And I couldn't tell the difference between the two patterns just by observation. But when we do the reconstruction to the heart, you see very different patterns on the heart itself. So very different patterns on the heart can generate very similar patterns on the body surface. And that's the lack of specificity and sensitivity of the electrocardiogram due to the distance from the heart. And it's not just the distance, it's the fact that the medium, the volume conductor, convolves the electrical sources in the heart. The Laplace equation, electric fields don't spread in straight line. So when you measure something by an electrode here, it measures the electrical activity all around the heart integrated, not at the point underneath. So you cannot make projections, and all the geometrical relationships are lost. And therefore, you can't expect that similar things on the body surface will translate to similar things on the heart. Okay? That's why we need to go back to the heart. And this is just a comparison to intraoperative study done by Windham. This is our non-invasive research study in all of the 7 people. And this is his study in 11 individuals who went through open heart surgery for reasons other than ventricular disease, like valve replacement. And he mapped it directly from the heart with socks of electrodes. And you see, these are the percentages of his patients that had breakthrough in different points. All of them had this right ventricular breakthrough, same here. you can see that the locations are very similar. Wherever he had them, we also identified non-invasively. You see the similarity is striking. The only place that is not similar is here. He had 0 breakthrough here, and we had over half of our patients or volunteers showing breakthrough here. And when we looked closely in the data, it turned out that he didn't have any electrodes in that region, so he couldn't measure it. This is again comparison to the chimpanzee, and Medispak showed in his paper electrograms, okay, electrograms from 4 points on the chimpanzee heart, measured invasively with electrodes on the heart surface. And you see a progression as you go from 1 to 4, from a small r, large S morphology, very small positive, large negative, to an RS morphology, and then it becomes more positive, and then finally a pure R wave or fully positive. This is one of our males, this is one of our females in the study, and you see very similar electrograms from location. We took these locations to anatomically correspond to the locations in the chimp for which those electrograms were shown. And you see the correspondence, RS, exactly like this, and the progression to completely positive electrogram at 0.4. So also a very good agreement. These are isochrones, non-invasive isochrones for 3 hearts in this normal study. First of all, you see that not all normals are the same. There is great variability between normals. For example, if you compare this heart to this heart, there is a breakthrough here, an area of early excitation. These are isochrone times. So there is an early excitation breakthrough on the left ventricular posterior here, but not in this patient, not in this subject. So normal. Similar variability is seen in the Dura subject. So not all normals are the same, and this is a misconception that has to be corrected. Normal hearts have lots of variability between them. But there are a lot of similarities between the hearts of Dura and the hearts that we have done non-invasively. For example, in this case, you see that there is a line of early activation, and here too, for example, this one. There is a line of early activation that is parallel to the left anterior descending coronary artery. Okay, so you see a line of early activation, and the same thing is seen here in the Dura study. And then last area to activate, blue is latest, is in the posterior basal area of the left ventricle. The same is in an invasive study. Here you have 2 points of early activation, anterior, perpendicular, not parallel, but perpendicular to the left anterior descending coronary artery. Same here in one of our patients. Okay, and the same here. All of these, 1, 2, 3, and 4 points of early activation are all reconstructed non-invasively in this patient, very similar to this variant of normal study in the invasive study. Okay, so far about activation. Now about repolarization. So repolarization is the T wave, and we can reconstruct T waves. And if we take the distance in time between, or the interval between activation time and repolarization time, this is called activation recovery interval, and it was shown to reflect the local action potential duration, because electrograms reflect action potential. The QRS reflects the rising phase of the action potential. T wave reflects repolarization of the action potential. So the distance in time between them is the action potential duration, roughly, locally. So we computed action potential durations, or activation recovery intervals. This one is from point 1, which is in the right ventricle. This one is from point 2, which is in the left ventricle. You see that the activation recovery interval is about 225 milliseconds, which is typical of human action potential duration. And there is longer action potential duration in the left ventricle compared to the right ventricle. There is a gradient of action potential duration of about 40 milliseconds between the 2 ventricles, and that has also been documented in humans. Repolarization is very different from depolarization. During depolarization activation, the heart potentials were very dynamic. Every millisecond something happened. A breakthrough here, a breakthrough there, everything changed. During repolarization, the process is very static, and you see that at the beginning of the T wave, and the middle of the T wave, peak T wave, the pattern is very similar except the amplitudes are increasing. So it's a very static pattern because the T wave is large. If you translate time to space, it encompasses most of the heart, and therefore there is not so much spatial progression. Another important thing is these are the recovery time isochrones. Okay, what does it mean? These are the times of recovery, just recovery, not activation recovery intervals, but recovery. Recovery depends on two things: the time of arrival of the action potential, that is the activation sequence, and then how long it takes to recover. It will recover after arrival and then recovery time, right? So this depends on the activation sequence. These are activation recovery intervals. Activation recovery intervals are obtained by subtracting the activation time or the arrival time of the activation time. And therefore, it reflects only the local repolarization properties and local action potential duration. Look at the similarity of the two. They're exactly the same for all practical purposes. That tells you that to a very good approximation, repolarization and recovery of the heart is determined by local repolarization properties, not by the sequence of activation. This is because under normal conditions, the action potential travels very fast, it utilizes the conduction system, and therefore activation of the heart as a first approximation compared to recovery time can be assumed and approximated as an instantaneous process. That's why these two are so similar. And this is a proof of this concept. The mean activation recovery interval for all of those 7 subjects were 235 milliseconds. Again, a very good action potential duration for her in units. And the apex to base, there is also apex to base dispersion of repolarization or RI differences in the LV alone. And we found that the dispersion of repolarization to be around 37 milliseconds, with the base having longer action potential than the apex. And that has to do probably with several things. One of them is differences in ion channel expression. For example, Gene has been exploring the different expression of ion channels throughout the heart, especially IKR, and they differ. And one of the possibilities is that there are different density of functional repolarizing channels in the base compared to the apex, or there could be also different loading conditions that acts to change the action potential duration. Okay, some abnormal examples. Right bundle branch block, RV and LV pacing, and atrial flutter. I'll go through those. So first of all, right bundle branch block. The right bundle branch block, what happens is that the right bundle branch of the conduction system is not functional. I showed you before that under normal activity, both branches are fed at the same time, and we create broad wavefronts that propagate from the endocardium to the epicardium in both ventricles simultaneously. If the right bundle branch of the conduction system is not functional, then activation will go first to the left ventricle and then slowly propagate from the left to the right ventricle. And it will be sequential, and activation of the right ventricle, instead of happening early, will now happen late. So here you can see the right ventricular breakthrough. This, okay, is the potentials on the heart with right bundle branch block 35 milliseconds after the beginning of activation. You can still see here only positive potentials, while normal breakthrough was at about 21 milliseconds, which we saw before for a normal subject with intact right bundle branch. Only at 49 milliseconds, much later, but twice the time, longer than twice the time, you start to see breakthrough and arrival of activation to the right ventricular epicardium. You can see this also in the isochrones. You see here that early, which is red, is all over the left ventricle. Late, which is blue, is the right ventricle. And in fact, there is slowing of conduction over the right ventricle. You can see here crowding of isochrones, and the base of the right ventricle, this whole area here, is very late to activate. It's also reflected in the electrograms that we reconstruct. You can see, for example, in electrogram 4, which is from this location here, that is on the left ventricle across from the right ventricle. In normal case, there is a QR morphology. Now, the QR morphology is followed by a negative late deflection and S morphology. As I told you, if you have an activation front going away from you, you'll see negative deflection. So now you have late activity going on in the right ventricle away from the point on the left ventricle, and it is seen from the left ventricle as a late negative deflection on the electrocardiograph. So it's all very consistent. Pacing. This patient, what we did was we studied 8 patients that have heart failure, severe cases of heart failure. And these patients are treated with a biventricular pacing device for what's called cardiac resynchronization therapy. What they do is they pace the right and left ventricle, and they program it in such a way that they optimize the mechanical performance of the heart in terms of cardiac output, if they can. Also see. But nobody knows exactly how it works, and we had a study of 8 people going on through this therapy, and it's now accepted for publication. Should appear in February. In any event, here I'm not talking about that study. I just wanted to show you that we can reconstruct the activation sequence and the details during pacing. This patient had 2 electrodes in his heart. You can see the image here is a transparent image taken with the CT, and you can see that one location of an electrode is right here at the apex of the RV. Another location is right here. You can see the lead, and the wire, and you can see the electrode, and this is its location. These are the potentials that we reconstructed during pacing from this electrode, and this is what we reconstructed during pacing from this electrode. You see that there is a very strong local minimum at this location. Well, what do you expect to see when you sit on a pacing site? When you sit on a pacing site, all you see is the activation front going away from you, right? It starts right where you are. So you see it going away from you. If you see it going away from you, you see tails of dipoles that are all negative. Therefore, you expect at the location of pacing to have an intense minimum. This is exactly what we have, an intense minimum, and we located this pacing site based on the location of this minimum to within about 7 millimeters of its actual position. This is also, by the way, is a good indication of how well we can locate arrhythmogenic foci. The focus of arrhythmogenic activity, focal activity, is very well simulated by a pacing electrode. Okay, so that's the minimum that shows that. Here is isocones, and you see that early, of course, starts right at the pacing site. These are all non-invasive reconstruction. For the other location, exactly similar results. Minimum at the pacing site. Activation now starts here. Red is early from the other pacing site. So we can locate pacing site and map ectopic activity from unwanted foci with good accuracy. Repolarization. That's interesting. Repolarization is very different. It's exactly the other extreme from what we saw in the normal. In the normal, activation of the heart was very fast because it utilized the conduction system, and therefore time of arrival could be assumed as simultaneous for all heart points compared to repolarization. Here it's totally the reverse. Because the activation starts from a pacing site, it doesn't utilize the conduction system. It's very slow. It takes very long to depolarize the heart. The QRS is very broad. And now we expect that activation will determine repolarization time. It's longer than local repolarization. So now you expect your pattern of potentials during your polarization to be exactly similar, the same, or close to, the one you had during activation, except with reverse polarity, because the T wave is reverse polarity to the QRS. It's exactly what we see. Look, this is local minimum during activation. During repolarization, it becomes a local maximum. This is local minimum during activation, becomes a local maximum during repolarization, just as the theory predicts. Atrial flutter. This is a patient that had chronic atrial flutter, a very common arrhythmia. And remember, in the normal case, activation starts from the sinus node and propagates in all directions, finally arriving at the left atrial appendage. In this patient, the arrhythmia is not focal, like I showed you before, but it's reentrant. And this patient, this is non-invasive reconstruction of this patient arrhythmia during the flutter. And you see here in black arrows the reentry circuit that drives the arrhythmia. You see that it goes down the free wall of the right atrium. It slows down as it crosses this narrow isthmus here between, it goes to the IVC. There's crowding of isochrone and very slow conduction. It then penetrates the septum, comes out from the septum near the Bachmann bundle, and then goes down the right atrial free wall. And this will continue over and over and over again. You can see many beats, they're all the same, and will go over and over and over again. This also radiates wavelets in all directions. There is one big one that goes around the IVC below, comes up again, and then collides with other wavelets that are emanated from the major reentry pathway, and they collide over the crista terminalis. Other wavelets are going in the direction of the left atrial appendage to activate it also last. So you can see that we can locate and map in detail, non-invasively, the reentrance circuit during the arrhythmia. If you want to ablate the arrhythmia, it's probably the best thing to do is just have a scar here and close the isthmus, and then the arrhythmia will not be able to survive probably. And also it shows all of the wavelets that are emanating from the reentry circuit, the collision between them, and the details of the activation during the arrhythmia. Another thing that we've done was to compare and validate this in patients undergoing open heart surgery. And what you see here is the same procedure as before. The only difference is that now we had 2 patches of electrodes, 100 electrodes on each, and they were put on the surface of the heart during open heart surgery. So now we had direct measurements from the heart. It's not as good gold standard as it was in the 10 torso experiments, because this is not done simultaneously, and it's done under different conditions. This is done under closed chest, and this is done under open chest. And there are many other differences, of course. But it's in the same subject, the same heart, not at the same time, not simultaneously, not under exactly the same condition, but still, I can show you this. Just shows the electrodes that were used on the surface of the heart and the operation. And these are examples. What you see in red are invasive electrograms from these different points here. And what you see in black are non-invasive electrograms that were reconstructed after the surgery, 4 days after the surgery, from the body surface non-invasive. And you can see that it's not exact, but the comparison is very good. There is great similarities, and basically the morphology, the gross morphology of the electrogram is very similar between the invasive measure during open heart surgery and the non-invasive reconstruction. And finally, I wanted to show you our first clinical case. That is, we did atrial flutter is clinical case, but that was because we were interested in studies. This was the first time that the clinic came to us to help them with a case. And that was published as a case report just this last issue, this November, just now. What it was an electrographic imaging of ventricular tachycardia in a young athlete. And the case is the following. The 29-year-old athlete was referred with frequent premature ventricular complexes, PVCs, on routine EKG. Okay? So he had premature, he's a very fit athlete, a soccer player. And he had premature ventricular complexes once in a while on routine ECG. He developed spontaneous sustained wide QRS tachycardia during exercise tests on a treadmill. And the ECG morphology during the tachycardia was very similar or the same as during the PVCs. Okay? They asked us, they had very difficult times to locate it. There were more than one focus apparently. Some of it was basal, some was apical. It was not clear to them using common catheterization technique where the focus was. And they asked if we can help them, and we said yes. And that was our first clinical case of somebody who was referred to us from the clinic. This is just to show the 12-lead ECG during his ventricular tachycardia while exercising, and you see, of course, the erratic rhythm and very fast ventricular tachycardia with a very wide QRS, indicative that the conduction system is not utilized. The conduction is slow. And here you can see our non-invasive reconstruction using ECGI. This is a map that was done using the CARTO method, that is an endocardial map that was done using a catheter, okay, to collect data from many PVCs. It's very difficult to do because, remember, you cannot do it during the tachycardia. Very hard to do. You collect data from many different premature ventricular complexes. It takes a very long time with the catheterization procedure. And then they weren't sure about the answer before. This was done after we gave them the electrocardiographic imaging. I'll tell you about this in a minute. But anyway, you can see these are isochrones that we reconstructed non-invasively, and we located the arrhythmogenic focus to this area here, which is in the left ventricular, okay, the left ventricular apex. So right at the left ventricular apex junction with the septum is where we located the initiation site and the unwanted focus of this arrhythmia. That was then confirmed by careful mapping that was done after they knew where to look. That was guided by this and confirmed that exactly that's where it was. They tried to ablate it, and it couldn't be ablated. It was temporarily seized, the tachycardia, but then it came back. Turned out that they couldn't do it from endocardial approach. And we said that it's epicardial, not endocardial, because if you see here, the electrogram from that location that we reconstructed is all negative Q morphology. It has a little area that indicates epicardial. If it were endocardial, you should see the activation from coming towards the epicardium. You'll have a positive deflection force. But because all negative, it tells you that it started from the epicardial location. So we said it was epicardial. At Case Western Reserve University, they couldn't do epicardial approach ablation. So the patient was sent to Boston, to Brigham, where what they do there is an approach through the epicardium. That was a method that was developed actually in Brazil by Sosa, who developed the method of creating a little incision here and pushing a catheter to get to the epicardial surface of the heart. And there they use this to map, and they map area of low voltages and the beginning of the PVC also from the same region that we indicated here. They try to do cryoablation. It's a sad story because you start to see all the clinical complications. They try to do cryoablation with a very cold probe to basically freeze the tissue, killing it not by heating but by cooling. But the phrenic nerve was exactly at that location where the ectopic focus was, so they couldn't ablate because they would have killed the nerve. So all of these limitations. Anyway, this athlete now is fine. He has an ICD implanted, he had surgery, and he's playing again with ICD. Okay. Interestingly, on the CT, what we saw was striking. We said it started from here, and look what happened. This is the location that ECGI predicted and identified the location of the arrhythmogenic focus. And when we looked at the CT again, we saw that it was a very, very obvious diverticulum. There's thinning of the myocardial wall. You see, it's like a bite was taken out of the wall. And that could have been either because of some developmental disorder, or more likely a viral infection that caused this to happen. Hopefully the viral infection is not continuing. But if that's the case, then this tissue here is very abnormal, and everything became very consistent because exactly to this location, ECGI located the focus of the arrhythmia. So that's our first clinical case. And you all know this building by now, which is very beautiful, and I'm very grateful that I'm here. And I wanted to just tell you who participated in these studies. So the major work on ECGI in humans, not before. Before that, there was a whole generation of students that worked on the tank torso experiments and so on. But in human was done by Charu Manhattan, Ping Jia, Raja Ganem, and Paul Liu. All of them were students at Case Western Reserve. Charo and Ping are still in Cleveland. Raja is working at Medtronic, and Paul is working at St. Jude. We send them, all. And then these are many of our clinical collaborators. Selma Intini, Aldo, who's a good friend, Markowitz, the surgeon who did the mapping with us during open heart surgery, a lot of fellows, and then Bill Stevenson from Brigham, and Pedro Brigada from Belgium. And here, we're continuing to work on this, and the students in the lab that are working on electrocardiographic imaging are Yang Wang, Shubham Ghosh, Dina Asper, and Leonard Lifshitz. Dr. Lifshitz, who's a postdoctoral in the lab, also involved. The clinical collaboration so far, Pamela Woodard from radiology, Edry from pediatric cardiology, Pete Fellis from cardiology, and Scott Nurse, who's a fellow in cardiology. And we're hoping that this list will become as big as this list. We've only been here for 14 months, and we're still room for growth. So thank you very much. Any questions to the speaker? Okay, I knew.
So I'm curious why you went straight from the tank torso to humans. Why you didn't go through, say, dogs, where you could have extensively looked at the effects of movement.
No, so we did. First of all, the heart beats also in the tank torso. The patient, you of course don't let them move, but the heart moves also in the torso. And we did studies in the dogs also, especially on repolarization. We published a study where we looked at dispersion of repolarization. In an open chest dog, what we did was we cooled a region of the myocardium to slow repolarization to create dispersion. We warmed a region next to it to cause decrease or it speeds up repolarization. So we got a region of high dispersion of repolarization, which we mapped directly from the heart, and then reconstructed and showed that we can locate the area of high dispersion very precisely. So we did that in dogs. The reason for the tank torso is that this whole method depends a lot on the geometry. And the human geometry to the heart is very different from the dog. The dog is very cylindrical, the human is not, and we wanted to have a geometry that approximates the human geometry. That was actually the exact geometry that then we employed.
So you have to make any adjustments for the different tissues between the heart and the surface to make adjustments for bone,
that's a
muscle,
good question.
and lungs and things.
Very good question. We're lucky because we did a lot of studies to study the effects of the torso inhomogeneity, like the lungs and the bones, on the reconstructions. It turned out that it only affects amplitudes of potentials, but not patterns. Okay, so we can include the inhomogeneities. You can get the heart, the lungs, the bone from your scans and incorporate them. It'll be a larger A matrix and more complicated solution, but it's doable, and we have it. It's part of our algorithms that we developed. But turned out that in most cases we don't need it, because what we're looking for is mostly patterns, not absolute amplitudes. And the patterns are not influenced by these inhomogeneities. Lucky.
So two questions. Two related questions. Do you think you need higher spatial resolution to really apply it clinically? And if you do, what would it take for, let's say, the number of electrodes to do that? Let's say to double the resolution.
It's very hard to double the resolution, and I'm not sure that it's really necessary because we can now locate pacing sites, for example, with 7 millimeter resolution. The way treatment is done is much more gross than the scale. And so for ablation purposes and location of pacing sites and pacing electrode, guiding location of pacing electrodes and so on, this resolution is probably sufficient. Now, resolution doesn't grow linearly with the number of electrodes that you use in the body. So we showed actually that we can dropped down. We started in the tank torso, we had 400 electrodes on the body surface. We dropped it down to 180 before we started to see any measurable differences. Okay, so at the 250 that we use, I think is enough. You can go up to 500 if you want to do resolution, but you're not going to get twice the resolution.
You had mentioned that there's some normal variation in the activation sequences. Do those change with like eating a meal or hormonal influences or?
I don't know, but Lina in our group now, see what we've done here was 7 normal young adults, all at rest conditions, rest heart rate. And most important, the most interesting thing is what happens when you double the heart rate. What happens to the heart when the heart has a function of rate. So now we're starting a study actually in 2 age groups, the 25, 30 years old, young adults, and 65, 70 years old, at rest, and twice the heart rate. And we want to see how they adjust, what the differences are, especially between the age groups. I think it will be a very important study. So that's just starting now. Lina is not here because she's traveling back from vacation. She's the one who's going to speak to the study.
I noticed that you didn't mention the AV node in your presentation here. Did you actually look at the AV node in one of your studies?
The AV node creates small potentials on the body surface, and they are absorbed in atrial activity and Purkinje system activity. It's very hard to get
So
the
the
AV
resolution
nodal
doesn't-
recording from the body surface, so we can't reconstruct the AV node activity. That's more certain.
So AV node re-entry tachycardia will not be.
Yeah, I don't believe. I think what we can see is what emanates from that reentrant tachycardia. If it involves the AV node and the atrial tissue, and it goes that way, like a Wolf Parkinson White tachycardia that involves the AV node and some other piece of tissue, it generates sufficient potential that we can measure on the body surface. What we can't measure on the body surface, we cannot reconstruct because we don't have data.
Just a practical question. So you started out by suggesting that conventional EKGs lack sensitivity and specificity. And so I wonder whether you envision this sort of approach as eventually replacing the conventional ECG, or is this too time-consuming, too expensive, what does it take to acquire the data?
It's hard, yeah. It's a good question. I can't, predict how it will evolve, but there are several answers to this question. First of all, this method is not expensive. It's basically electrocardiograms. CT, but every place has CT. It's available and it's in routine use in almost every hospital. So it's not difficult to apply this in any hospital to anybody who wants to apply it. Now, will the general population go through screening with this? I don't think so. But for example, let's say that you genotype people with long QT syndrome. You know that a family has long QT. Out of 5 siblings, 1 will have arrhythmias and will die, and 4 will not. I would say for that situation, you would like to take them and image their substrate and see if you can find out who is prone and who is not, so you can use protective measures. People post-MI, myocardial infarction. Many people post-MI, 5 months later, 6 months later, some of them will have an arrhythmia and sudden death, and many will not. We already have some assumptions about this, and in fact we're getting into a study of myocardial infarction with Pam Woodard in comparison to MRI, but we assume, our hypothesis is that there are different substrates in different MIs. And an MI that is uniform and dead is good. An MI that has many discontinuities and islands of surviving myocardium can generate arrhythmias. And those are the kind of things that you saw in the tank torso. We could find out all these little notches on the ECG existing of surviving myocardium. So if we can only identify patients at risk among the populations that already have risk, like MI, hereditary arrhythmias and so on, I think that's important to do. The other application, of course, is, for example, to look at the effects of drugs. and any treatment over time. You can use this to see if the drug is helping, if it's pro-arrhythmic by increasing dispersion, or anti-arrhythmic by decreasing dispersion in the same individual. You can use this to play an ablation and to, in the future, maybe focus energy from the outside, like high ultrasound energy, so that you don't have to use catheters to ablate the arrhythmogenic substrate. If you know where it is, maybe you will be able to aim, like like they do now in tumors. And so there are many things that could be done with this to replace ECG in the overall population now. Except that now we also have a method to get the geometry without CT, and maybe that approximation could be used more widely. If you do that and you identify somebody that needs to go through further thing, then they could take the CT and go through the whole procedure. But that remains to be seen. It also, by the way, could be used, I think would be for us, what's interesting us, and I think is exciting, it could be used as a research tool to study mechanisms of arrhythmias in people, where the substrate is very different from, as you know, the animal models. The 5-day-old infarct is an important model, but it's not the same as the infarct in somebody who had 20 years history of coronary heart disease. So it's important to study mechanisms of arrhythmia, and this gives us the first opportunity to do this. Maureen.
Is the inverse problem more difficult because you have non-conducting tissue? Like if you could put the heart in a saline solution and then measure it from the outside, is that actually more difficult or easier?
The ill posedness is not a function of the. In fact, when you have homogeneous medium between the heart and the torso, the conductivity cancels in your mathematics. It doesn't even appear. So the conductivity is not apparent. It's basically the distance. And so if you develop it into a multiple expansion, right, you go like 1/r to the n+1, you measure any small error on the body surface, it will be amplified as r to the n+1 when you go in. So every small error will cause very large unbounded error in the solution if you don't constrain it or you don't use the method without inverting the matrix. So it's really the distance that is doing it.
Well then, can you do sort of an inverse problem from the epicardial surface and get the endocardial potential or
No.
the M cell layer?
No, because you cannot, if you remember in one of my first slides, I wrote Laplace's equation as governing the electric field. Laplace's equation assumes that there are no active sources. So you can get to the surface of the heart, but you cannot penetrate the muscle because the muscle has active sources and does not satisfy Laplace's equation. It satisfies Poisson's equation, which is a whole different story. Yeah.
So you said that the further the distance, the more inaccurate. So how robust is this to...
I can hear you.
The further the distance, the more inaccurate it is?
It's not the more inaccurate, it's the more, there is more effect of the distance on amplifying inaccuracies in the measurement.
Okay.
So you regularize, you have to regularize it. You know, the regularization that you do, that you impose, has to take into account the distance.
So how robust is this? If you had a very large patient, someone who was very overweight,
No.
does it make it more difficult?
No.
Okay.
Okay, well, thank you everybody, and I thank the speaker.